So let's start talking about what do you mean it's not 100%. This is a lecture going over how to calculate percent yield. The quote we have, I knew I could control one thing, and that is my time and my hours and my effort and my efficiency. So this whole lecture is going to be about efficiency. We're talking about percent yield. The learning goals, students will understand some of the factors that restrict experimental yield. So we're going to look at what limits how much we can actually get produced. We talked about limiting reactants. We're going to talk about a few other things that kind of hinder how much we can produce. Number two, students will be able to calculate the percent yield. So we actually want to be able to answer percent yield questions. So let's dive right in. What we should already know. Reactions are limited to the amount of reactants. This is where we get into limiting reactants. How much we have depends on how much we can produce. That's the whole law of conservation of mass. We can't produce any more than what we have. And the limiting reactant, it limits it. Running out of one reactant halts the reaction. So when we use up all of the limiting reaction's done and it stops. And then all reactants must be present for the reaction to occur. So once we run out of one, the reaction stops. We can't do anything. Now, looking in the lab, what we did there are times when you won't get as much product as the equation and math tell you that you should. Very few chemical reactions are 100% complete. So, rule of thumb is normally we're not going to get 100%. We get around 98, 99, we're doing really, really good. But not all reactions are going to be 100%. So, nobody's really perfect, and that's the whole we're not going to get 100% thing. Reactions almost never react 100% of their possible yield, so we're not going to get 100% of the product. A lot of reasons go in on that. Here's a good example. Let's see, we have the reactants and they're bonding together and everything else, and well, they just don't get on the same side. For a reaction actually to happen, the atoms actually have to touch each other. They have to come close to each other for a reaction to happen. And if that doesn't happen, then guess what? You're not going to produce anything. There's not going to be a product, and you're not going to get 100%. Okay, other factors, the reactions depend on a lot of different things. Temperature. Okay, temperature has to deal with it's increasing the rate of collision between atoms. We'll talk about temperature and kinetic energy a little more later on in a couple different units. But the one thing that we need to understand is that temperature really it's kind of related to the kinetic energy. So how much it's moving, and so the more it moves, we increase the rate that it's moving. It'll increase the collisions. Looking at pressure and volume. Anytime that we change the pressure or volume, it changes the space. And in a confined space, it makes more collisions, and the right molecules colliding with each other, and they're more likely to hit each other if they're in a tinier area. A catalyst. Catalysts are great to use, and they can increase how much we produce. A catalyst is just something that speeds up the reaction. It helps the reaction along. It doesn't really have anything to do with it, but it helps it and speeds it up. A medium, what the reactions are in. Is it an aqueous solution? Is it a gaseous solution? So whatever the medium is, that can affect the reaction. Number of reactants and concentration. So anytime if we're really concentrated, or is it not so concentrated, it's weak. And then lastly, the number of products in the concentration. So the products can block formation of new products. So basically, a product gets in the way, and it's not allowing those other particles, the other reactants that kind of get in there to actually bump into each other and actually react. So let's jump into an example. Example A1, it says that doctors are in desperate need of 2-acetobenzoic acid, and a chemist has 2.5 kilograms of salicylic acid and 1 kilogram of acetic anhydride. What can be done to maximize the yield of the reaction? So here's a reaction, a lot of big words and everything else, but basically, what can you do to increase the products of the reaction? Well, we can talk about a lot of those things, or what we just talked about. We can increase the temperature. Okay, if we increase the temperature, these guys right here will collide more, and so therefore it'll produce closer to 100%. We can decrease the volume, so make the space smaller. They bump into each other more. Increase the concentration, and dissolve it in a solution so that they're actually colliding a lot easier, and they're more concentrated, so they're more likely to hit each other. And use a catalyst to speed it up. And then make sure that we have a good method of removing the product after the reaction has occurred. So we got to be able to get it out of solution or actually recover the product. So those are just some things that the doctors can do to speed up the reaction, actually get closer to 100%, and be more efficient. Looking at our next reaction, our next example, it says explain the role of sulfuric acid in the reaction below. Well, we're looking at this, and sulfuric acid, since it's over the arrow, we know that it is a catalyst. Okay, and this is basically what's going on in our stomachs. And we see that we have our hydrochloric acid right here, and we're looking at the reaction that's taking place, and we can see that that sulfuric acid is going to act as a catalyst. Really, what is actually happening is the sulfuric acid is a catalyst that removes that hydroxide. So it moves this hydroxide right here, and from the molecule, and forms a positive for that carbon, and this carbon attracts the chlorine to stabilize itself and allows the hydronium ion to reform with the sulfate to bring back the sulfuric acid. That's what's happening. What we really need to know and focus on is that, hey, this guy's above the arrow. It's a catalyst. It's going to help speed up. So we know that we're not going to get 100% because there's a lot of factors that go into play. But we want to figure out how efficient a reaction is. An example, when you can look at a bunch of different stats on, let's say, basketball players, that's what we have here, and you have a bunch of different stats, and you can try to look at different things to see how efficient they are. You can see points per game or something like that, and that's how you can find efficiency for athletics and basketball players in this case. But when we're looking at this, we have two different reactions. We need to be able to do the same thing. Which reaction is going to be more efficient? Now, both of these reactions can produce sulfuric acid, but the second one is more efficient. So the second one is more likely to produce sulfuric acid more efficiently, and we're able to get more of our product, okay, closer to that 100%. So that is where percent yield comes into play. Percent yield gives us that quantitative value that we can actually say, hey, this reaction is more efficient because it has a greater percent yield. So when we're calculating percent yield, this is how we do it. We start with the balanced equation because, yes, this is stoichiometry. Always starts with a balanced chemical equation. We identify the limiting reactant and calculate the maximum amount of product that can be produced, which that's the theoretical yield. We measure the mass of the product that's actually produced. Okay, I would say that this is done in the lab. So you're actually recovering it. It's actually sitting in front of you. You actually put it on a balance. Okay, that's what you get in the lab. And then you just use this formula here. Percent yield equals 100 times our actual, which that's what we get from the lab, and then divided by our theoretical, which I would put next to theoretical, math. You have to calculate the theoretical yield. Okay, the actual yield comes from the lab. The theoretical yield comes from math. So let's go ahead and jump into an example. It says, example B1, 1,500 grams of zinc is available to react with 200 grams of copper 2 sulfate. This is the resulting yield of copper is measured to be, so this is what we actually measure. What is the percent yield of the reaction? So remember, if we have our actual, because it says this resulting yield of copper is measured to be, so that's what we actually have. That's our actual yield. The only thing we need is our theoretical yield. So we need to calculate what our theoretical yield is, and we do that by starting with our limiting reactant. So on this, we have to find our limiting reactant. We always start with a nice balanced chemical equation, because that's what all stoichiometry starts with. We've used this reaction a lot before. We used it in the lab. It's one that we should be used to. So copper 2 sulfate. We have our copper, which it's 2 sulfate, SO4, which is 2 as well. So we'll get our equation of copper 2 sulfate is CuSO4, plus we're adding zinc metal. So it's just Zn. And they switch places. Now, all the oxidation numbers are the same, so everything's just going to be a 1. So we have copper plus our zinc sulfate. Okay, so when all the oxidation numbers are the same for every single thing in the equation, you're not going to have to balance it. It's all 1s because they're already all balanced. So going into this, since we have our balanced equation, now we can actually start with the problem. So we'll have 1,500 grams of zinc, and we have 200 grams of our copper 2 sulfate. Now, just looking at this, since all the ratios are 1 to 1, in this case, since there's so much of zinc and so little of copper 2 sulfate, more than likely copper 2 sulfate is going to be our limiting reactant. But let's figure that out. So zinc is 65 grams per 1 mole, and in one reaction we have 1 mole of zinc. So we go ahead and multiply and divide, and we get 23.08 in a reaction. And then 200 grams of copper 2 sulfate, which copper 2 sulfate has a mass of right around 160 grams per 1 mole. And again, it's 1 mole in one reaction, which we multiply that out, and that's going to give us a much smaller number, which is 1.25 in a reaction. Okay, so that's going to be our limiting reactant. So we start there. We really don't need zinc anymore, so we'll get rid of it. We need the space. So if this is our limiting reactant, let's find our theoretical yield. So we start with our 1.25 in a reaction, and we're trying to find, since it's the resulting yield of copper, so we're looking for copper. So in one reaction, we have 1 mole of copper, and then all we have to do is just get it to grams, because we see that our actual yield is in grams. So 1 mole equals our molar mass of copper is 63.5 grams. Multiply that out, and we should get a theoretical yield of 79.4 grams in a reaction. All right, not in a reaction, but 79.4 grams of copper, which is our theoretical yield. Now, this is a place where you can kind of put a note. Your theoretical yield should always be more than your actual yield. If it's not, then you did something really wrong. So all we have to do to finish out the problem, our percent yield equals 100 times our actual, which is 70, all divided by our theoretical is 79.4. So divide first and then multiply by 100, and we should get right around 88.2% yield of copper. All right, another example. It says the combustion of propane is determined to produce 93% of the expected carbon dioxide. What mass of carbon dioxide is produced when 200 grams is combusted in 100 kilograms of oxygen? When we're looking at this, it told us what the percent yield is. Okay, remember that we can always calculate the theoretical yield. So the problem, what it's asking for is it's asking for, well, what's the actual yield? So if I know that this reaction is it's 93%, that's what I'm going to get. That's normally what happens. Then how much is going to actually come out of this? Now, one thing I'd pay attention to, we see that this is in kilograms, and it's a huge number. So we have not just 100 kilograms, that's, we think of it as 100,000 grams of oxygen. So if I have 100,000 grams of something and then I have something with only 200 grams, what do you think is going to be the limiting reactant? Well, obviously it's going to be our propane. Okay, so since we can do that, we've already determined, yeah, definitely going to have excess oxygen, which we should, because there's oxygen in the air. We shouldn't ever run out of that. We have 200 grams of propane. All we need to do is calculate the theoretical yield, and then we'll multiply it by our 93%, and that will give us our the actual yield that we should get in the lab. So work it out. We have 200 grams of propane, C8.3. Okay, and one thing that we always have to have no matter what is we got to have our balance equation, so we can't forget to do that. So we have our C3H8 plus our O2 produces CO2 because it's a combustion plus H2O. So to balance this out, we go ahead, we have 3 carbons. We need 3, so we put 1 right there. We have our 8 hydrogens, so I'll put a 4 right there. Look at our oxygens. We have that 3 distributes, so we have 6 plus that 4 distributes, so 6 plus 4 is 10. That works out because we can make that 10 on the other side. So there's our balanced chemical equation. So when we're working this out, all we're doing is trying to find the expected carbon dioxide. So you can think of it this way: we're going from our 200 grams of this to our carbon dioxide, and we can skip the step where we find out how much is in the reaction, because we already know that the 200 grams of propane is the limiting reactant. So from here we can just go ahead and say, well, it's just a gram to gram conversion now. So we need the molar mass of our propane, which we find that out to be right around 44 grams is 1 mole. And we look at what's the mole ratio between these two guys. It's 1 to 3. So 1 mole of our C3H8 equals 3 moles of our CO2. Okay, not done, because we need to have it in grams, because we want to find out what's the mass of carbon dioxide is produced. So we go from moles back to grams, which carbon dioxide has a molar mass of right around 44 grams for CO2. So multiply everything out, and we should get something right around 200 times 3 times 44, all divided by our 44, and we should get something right around 600. So we get 600 grams, and that's how much CO2 is produced. So when we're looking at this, all we have to do here is we have 600 grams that can be produced, 93% of it. So all we have to do is, since we know what the percent yield is, we just multiply our 200 times. And remember, whenever we multiply by a percent, what do we always have to do? Move the decimal. So we multiply by 0.93. And we should get 600 times 0.93. And we should get something right around 558 grams should be our actual yield that we get.